Welcome, everyone. And today we're going to continue with our implementation lecture series. We're going to walk you through a facility location problem for COVID healthcare facility and hospital capacity expansion issue. I put this in the modules and course module lecture 4 in the implementation portion. Okay, so solving integer programming with Gurobi Python API part 3. Okay, let's go to our notebook, Jupyter notebook. It's COVID-19 healthcare facility capacity optimization. This problem we're trying to determine the current hospital capacity may not be enough for upcoming epidemic for COVID in the next few periods. So we're going to satisfy the demand from COVID-19 patients for treatment, and we're trying to minimize the cost for operating temporary facility. Okay, and predict the allocated patient from specific county and to a specific healthcare facility, how I divert the potential demand, which is potential capacity requirement, into the temporary, from the current existing facility to the temporary expanded facility. Okay, the problem description. We total have 9 counties and the hypothetical California area, okay, and they reach full capacity due to the surge of the COVID-19, for example. Many hospitals consider creating temporary facility and increase their capacity to handle increased prevalence for COVID patients. In this example, we focus on 9 counties in California. Each county has existing facility to treat COVID patient already, and also has the option to build a temporary facility to increase the overall capacity handling COVID patient. Okay, and here are the temporary data and give to you. And for each one of the 9 county, and here is their coordinates on the map. Okay. And then their demand for, based on the percentage of COVID cases require hospitalization. These are the forecasts, okay? And this is a per day demand. And the average number of day and COVID patients stay in the hospital, okay? And here is the data. For we have a demand, we can estimate the demand for each one of the county based on their population and their current prevalence, meaning the infected population. Also, for the current existing facility, we have 14 of them, and they have a capacity associated with those 14 existing facility, and these are the second columns are their coordinates as well, and then the current capacity was calculated based on 80% of their capacity in that sense. Okay, here we have consideration for temporary facility, which needs to be expand. And here we have actually another 7. Okay. 8, actually 8 of them, to potentially build temporary facility and to treat 100 COVID patient is about $500,000 each. Okay, so the coordinate of these 3 tables are in 10 miles, and we assume that each increase of 10 miles of distance has a associated travel cost for $5 per mile. And this is the goal of this problem, is trying to identify the temporary facility in order to accommodate the demand for treatment by the COVID patient, and also this is trying to minimize the total cost of patients driving distance existing facility to the temporary facility in that case. So here we have proposed a mixed integer programming problem, okay, and trying to achieve this, several decisions. And first, how to best utilize their capacity, okay, which facility cover which portion of the patient, whether to build a temporary facility and at the potential temporary location, how the patient from the county should be allocated for various existing and potential facility and to provide the best treatment. Okay, this based on a paper, okay, by Cleese and Bynum. We start talking about the mathematical part, the model description portion. First, I have an E as an index for all the existing healthcare facility. T represents the indexes for the potential or temporary healthcare facilities and location we can actually provide. Okay. Several parameters we need to do is the first is the distance from the county to the facility. Okay, distance from county to the facility. So from county C to facility F. The demand for each one of the county C, and for that demand, we need to satisfy. And the capacity, number of people that can be served at a particular location of a facility, which is capacity of F. D cost is the $5. In that sense, is cost of driving 5 miles. And we will have to using a subroutine to calculate the distance between two locations and using that as a basis to calculate the traveling cost. The cost of building a temporary facility is about $500,000 in that sense. And also we can add, okay, extra capacity to the temporary facility at a very big cost, okay, a large amount of cost. Here we're using a big M, and we're trying to prohibit that happen, but potentially in the futures, we can adjust this big M value in order to see if those temporary location can be increase their capacity as well. Right now, I think they are all 100, okay, 100 patient. We have 3 decision variables involved. First is the binary variable called YT. YT is the 0 or 1 if I want to build a temporary facility at the location T, okay, 0 otherwise. X is is the service variables. Basically, X is from a county, how many people or number of people served by the facility F. So that means for each county, the patient can be covered by multiple facility in this case. So this is a typical capacitated facility location problem. Finally, the Z is the extra capacity added to the temporary facility location K. So this Z maybe has a prohibitive cost. So our objective function is the 3 terms, and based on these 3 different decision variable. First is is the cost, okay, times the distance between the county to a specific facility. So X is the number of people actually served for that particular facility F. So X is number of people in county C to serve at facility F. The total cost is how many temporary facility I want to add. Each one of them is $500,000. So here is the second term. The third term is, do we want to increase or the capacity for the temporary facility with currently a big M, which is a large number, and trying to not let this happen. Got three type of constraint. First is the demand constraint. All the population has to be served on the county C, and for all the facility covering that particular county. So summation of F equal to F, capital F, which is set of a facility, and C county is C, and X is the number of people in that from that county served on the facility, and right hand side is the total demand of that county. We separate two other constraints. One designated to the existing facility with a capacity. Capacity of the location of a facility cannot be exist, so have a cap. So we don't have any option at this point to increase the capacity for the existing facility. However, we're trying to set up a new temporary facility, and also each one of a temporary facility has a cap as well, the capacity as well, which is 100 patients. And we have an option also to increase additional, we call it extra capacity, and that be covered by the decision variable called ZT. Okay, T is a temporary facility index. All right, here we start running our program. So first we import some of the Gurobi Python API library, and here we have some additional library. One we call it iteration tool called product, which is inner product, calculate inner product for two different vector. And the math library, we're trying to import the square root function. Okay, first we define two so-called helper functions. The first function is calculate the distance between two locations. As we look at our data, we're given a coordinate, is X and Y on the map. Okay, for county who have a demand for the existing facility with known capacity for the temporary facility. Also, they have the coordinate. For between each one of a county and to either the temporary or existing facility, we have to calculate the distance, and then also we can use that as a base to calculate the traveling cost for the customer. All right. So index for the county, we call it counties, okay, and this is from 1 to 10, so we have 9 of them. An index for the, this is the second helper function, we call it solve COVID facility. It's basically our main function, and to solve the entire problem. Second index we use is the facility, as we call it facilities Perl form. We have a total 24 facility. So we have 14, actually we have 14 existing one and 10, actually 8 existing one. Okay, so here what I have is we building the existing facilities with their coordinate and the capacity. This is the input data. Okay, I give it now, number 14. Then we have 15 to 23rd total, and for the temporary facility with their coordinates, and T coordinate, T capacity, which is temporary facilities locations and and capacity. So these are the two so-called multi-dictionary. Based on the number is the facility number, coordinates, and capacity pair. All right. So we've seen this a couple of times before. This one is a little bit more complicated. So since we have to calculate so-called binary costs, binary variables, we have continuous variables, and we have also the travel distance to carry with. It's a little bit involved. So we rely on our past experience to get familiar with the index syntax of this program. So total cost for driving 10 miles is $5. And total cost to building set up a temporary facility is $500,000. Here we can calculate the key parameters. We're going to add, since I'm going to add another dictionary called F coordinates. F coordinates is including all the existing facilities coordinate and adding all of the temporary facilities coordinate into this. Okay, so here, this one we're going to increase a pair of coordinates and facility into, inside the facility. So it's a pair of a C for county and F for facility, which is facility is range from 1 to 24, actually 23 of them, 1 to 23 basically, okay? So county is from 1 to 9, so I have 9 different county. 8 different county, I'm sorry. All right, let's go back here to, first is compute all the parameters and for the preparing for our models, and we're going to do the county and the facility partition, so it's a pair index. We can calculate for each one of the county to the facility and calculate their distance. Okay, so for C with the county and F with their facility and both location, I can use that to calculate the distance. So I put it into a distance dictionary right here. It's indexed by county and facility and give the distance of the so-called from to distance map. If you want, you can actually print out the distance and see how the actually the dictionary was formed, and once you execute this. All right. Once we've done this preparation work, it gives the input data for the coordinate and the capacity for either existing facility and the temporary facility, and some of the traveling unit travel, 10-mile travel cost, and the setup cost for a temporary facility. We're ready to set up the Gurobi model. First, we're going to create a model from Gurobi Pi, and we'll call it model. The model name is COVID temporary facility location, using an abbreviation M as a handler. So I'm going to using M. I'm going to add a three decision variable. One we'll call it Y, which is a binary variable, okay, and we'll call it temporary variable. Either I'm going to set up temporary facility YI or not, okay, 0 or 1. This is binary. Second is the patient coverage. So the assigning COVID patients for county C to facility F. So it's a pair of CF right here. We've done it right here. For each pair of a county facility pair, I want to have a XCF. And they are continuous variable, represent number of patients actually covered by that particular facility from that county. And we'll call this particular variable called assign, and of course its abbreviation is X. Z is the extra capacity for expansion. It's based only on the temporary index, and they are continuous. They're continuous variable when we call this variable add capacity. Of course, we have a big M, okay, the 10 to the ninth, okay, as one of big M. So we're basically trying to force Z to 0 unless it's necessary. And when later on, we're trying to show you how the big M can be changed if the current solution, current assignment is not be able to satisfy the demand, total demand. Set up our objective function, okay, actually 3 parts. The first part is the distance times the cost of traveling and times the XCF. XCF is population actually covered from county C to facility F. So for C and F are in the CF matrix, okay? Second term of objective function is the total cost, which is $500,000 times the binary variable y, summation of y. Summation of y, all the, how many we want to set up with. So this problem is a little bit looks like a minimum cost assignment problem. Also is looks like a facility location problem, set covering problem as well. So here we're trying to demonstrate the basic models we have been introduced so far and before, and now can be mixed and combined to building new model for your specific application. Of course, the third terms of our objective functions, the big M times the Z, sum of the Z. So we basically do not want to the extra capacity to happen unless it's necessary. So we give a very big penalty. Later on, we can change this penalty and then see how the extra capacity can come in to help. We have a scenario to tell you that. And my objective function is minimization, okay, for the objective function. And we have 3 separate constraints. The first constraint is the demand constraint. So summation of XCF, okay, and total for F for a facility, and for all the facility, okay, F, summation of XCF is for all the facility from that county has to be equals to the demand from that county. Okay, so this is what we call a demand constraint. Okay, so quick sum is basically summation of F. F is in facility in that case. All right. That's a demand constraint. Second is existing facility constraint, capacity constraint. So sum of the XC from E. E is existing facility number. C from the counties, which is the demand coming from. All the county assigned to that particular existing facility has to less than or equal to the existing facility's corresponding capacity. Similar things we do for the temporary facility. So sum of the C time C dot T sum of XCT, C is from county, T is from the temporary facility, and C is in county, and minus ZT, T is in the temporary facility. Z is the expanded capacity. Has to be less than or equal to the capacity of that temporary facility multiplied by Y decision variable. So that means if Y equals to 0 and this right-hand side becomes 0, so we're not allowing any population patient to assign it to that facility. If Y equals to 1, then that activates the right-hand side of the capacity of 100 patient in that sense. So this is what we call the temporary capacity constraint. We have a chance to using Z as expanded capacity. Finally, we can use the round optimization to solve the problem. And the rest of a part of this subroutine is just print out the solution, basically. Okay, so the cost, temporary facility cost, how many? So this is the first part of the actually second terms of your objective function. This is patient allocation cost would be the first term of your objective function. So here we have listed it out separately because in our model this time, we kind of prevented the expanded capacity to happen. So pretty much the third term is going to be 0 in our case. So we only print out the first two parts. Then we print out which one of the temporary facility is being used or being built, okay, or suggest to build. And also we're going to see if the increased temporary capacity is happening or not. Okay, and demand satisfied for each one of facility, we can show you how much demand is satisfied by each one of the facility. And in that case, basically calculate the X, okay, XCF. Okay, XCF. All right, finally, total demand satisfied of facilities, and we have accumulated portion. So I'm going to run this definition, and since this is just a subroutine, it won't execute anything until we start a base scenario. The base scenario is I'm giving the input for the county. I tell you why, because I put this, we put this first information, counties, coordinates, and forecast demands in min loop instead of subroutine, because later on we can change this. And for example, if we're forecasting there's a wave of a new virus variants coming up, and the demand for hospitalization will be increasing based on the current forecast, and how our facility decisions are going to change. Okay, so this is the portion we're given the coordinates and the demand for the counties. Then we're call this subroutine solve COVID facility, actually optimize everything. Sorry, I forgot to run a definition for that. Throw me an error. This distance calculation was not calculated. Okay, so 68 milliseconds, we finished the whole thing. And to solve with 216 continuous variable, 9 integer variables for yes or no. And okay, we have using a 3 Gurobi card, 1 of a mixed integer rounding count, and 1 as a relax and lift. And you can check the Gurobi's manual what those cards mean. Okay, total 134 nodes are exploited. 711 simplex iteration was executed, and in terms of 500ths of a second. Okay. So total objective function solution and optimal solution found. So this is the best objective function found so far. And these are for each one of the node exploration and fathom how they starting to figure it out. Of course, finally, we calculate the cost. Okay, we actually opened 3 facility, I think, temporary facility. Total cost will be $1.5 million, and this is the travel distance cost for the patient. Okay, and we suggested to open location 15, 17, and 18 location and to serve. Okay, so how many patients? Okay, is covered in facility 1. How many patients covered in each one of facility 2, 3, 4, 5, 6, all the way to 15, 16, and these are the temporary facility are open. So there are several temporary facilities, 19, 20, 21, 22, 23, are not used, as not recommended to set up. All right, so there is no no capacity expansion for all the temporary facility in that case. So for each one of the facility we suggest to open, there are some of the how many patients are covered by these facility in that case. So this is one base scenario. The next we're trying to do is if we kind of anticipated there will be an increase of hospitalization by 20%. The CDC announced as a new virus variant showed up, and it could have increased the infection rate. We call the basic disease reproduction rate increase. So in terms of original, maybe 1 to 2 people, now it's 1 to 7 people transmitting rate. So the disease reproduction rate went up many times, and we anticipated this will be have an impact on our hospital capacity. The percentage included 5% of buffer capacity accounted for variability. So here what we do is we're trying to do the forecast portion for the county by 1.2. So it's 20% increase. This is very simple. And then we resolve the problem again. Okay, so we can resolve the problem, and these are the plan to the facility. So it's $4.5 million setup cost. We need to utilize all the temporary facility available to handle the current situation. So this is basically what we have so far, trying to if the so-called if the potential demand, forecast demand increase. But you can also start exploring, how about we have extra capacity expansion. The big M numbers we have is instead of 10 to the minus 9, and maybe we can double the cost, double the facility. Temporary facility usually are representing a mobile treatment unit, and with some tents or temporary inpatient area, or we call the ward area, for the isolation and quarantining of the sick patient. And can we double that capacity using another $500,000? So these are the possible expansion we can, and can you also see we can explore when the capacity go up. Okay, when the capacity go up 20%, 30%, 25%, 40%, how that impact your healthcare system. And even some people can expand this using direct link to so-called disease transmitting ratio, or called a disease reproduction ratio. But that reproduction ratio basically means is the number of increase on infected people divided by number of recovered people. If the people got infected really quick, and also the patient got recovered real quick, the disease may not be having an effect. So we're using this ratio as a so-called disease reproduction rate. And with that, also due to the variance of the virus, the hospitalization rate, it may be different. Maybe we can use some kind of search and algorithm to find out within certain type of what we call the R0 and hospitalization portion, and we can using the optimization mechanism we designed right here. So here this example, just giving you a base models and some of the possible scenario you can change, and to find out, see if your healthcare system can handle the upcoming potential pandemic. And we're going to conclude this lectures here, and maybe we're using some exercise or homework and exam to demonstrate how this type of model can be expanded and modified and enhanced. Okay, we'll see you in the next lecture. Bye-bye.